TCP guarantees delivery and is a connection-oriented protocol. When a TCP message or packet reaches its destination, the receiving device sends an acknowledgement. If it does not receive an acknowledgement, it will resend the data or throw an error to the application. UDP is much faster than TCP because it's a connectionless oriented protocol and does not guarantee delivery. It just sends the data and assumes it arrives. Thus, TCP guarantees delivery where UDP does not. Google, though, has developed a new protocol called QUIC, Q-U-I-C. QUIC is mainly used for web data. QUIC uses multiplexing to send the data. Multiplexing is the use of multiple streams to send data at the same time. This way, if an error occurs, it just has to resend and fix the one stream while the rest of the web page or data is free to continue on the other streams. Whereas with TCP, everything stops and waits until an error is fixed. So TCP guarantees delivery, UDP does not guarantee delivery and is fast, and QUIC is almost as fast as UDP, but it guarantees delivery. So it is a merger of TCP and UDP. And Google is trying to get that set as a standard to where everybody starts using that instead of TCP. Here are some of the main application protocols that will utilize TCP IP. You got web, HTTP, HTTPS, email, SMTP, and then POP or IMAP. So SMTP, that sends the email. POP and IMAP are what read the email. RDP is remote desktop protocol from Microsoft, and then Telnet is an old way to connect to a computer. It is not very secure, and Secure Shell has replaced that for use. You should use a Secure Shell or something similar for computer control. FTP, File Transfer Protocol, SMB, Server Message Blocks, and then Apple File Protocol, AFP. These are some of the main applications and protocols used for TCP IP. Also, you have LDAP, Lightweight Directory Access Protocol, of which Active Directory, used by Microsoft, uses a version of LDAP. And finally, the Simple Network Management Protocol, SNMP. Next, we're going to cover some of the devices that make up our local infrastructure, such as desktops, hubs, switches, bridges, other network devices, and cables. And so we'll go into more detail on each one of these. Switches are how most devices are connected together on a local network. You can use hubs, but hubs are not suitable for today's high-speed networks. Switches operate at layer 2 of the OSI model and layer 2 of the 5-layer TCP IP model. Switches work at layer 1, hubs work at layer 1, the physical layer. Hubs receive a signal on one port and send the signal out on all other ports, whereas a switch receives a signal on one port and only sends it out on the port that has the destination device connected to it. A switch uses and tracks the MAC addresses of devices and what port they are connected to. If the switch cannot find the MAC address in its table, it will then and only then send out the message on all ports to try and locate the device. Once the response comes back, it will add that MAC address and port to its table so that the next time it will just send out the single port that contains that device. There are two types of switches, a managed switch and an unmanaged switch. Unmanaged switches are cheap and inexpensive and are mainly found in homes and small offices. Managed switches are found in most networks that are supported by IT professionals. Managed switches allow for configuration and easy monitoring. Managed switches also allow you to segment the switch into multiple virtual local area networks, or VLANs. This can allow you to reduce network traffic on each network, as well as provide for better security. Reasons to add a switch include adding more ports for the ability to add more devices, to regenerate the network signal to overcome cable length issues. Ethernet can only go 100 meters without having the signal regenerated, and a switch can do this for you. Another reason to add a switch is to manage and reduce network traffic. This graphic depicts that a hub sends a request out every single port, whereas a switch will send out the request only through the one port that has the destination device. This depicts that with a managed switch you can create multiple networks. In this case, the switch was divided into two networks, but it could have been more than two. Because the switch has two separate networks, you need a router in order for these machines on each network to talk to each other. Normally, all devices on a switch are in the same network and thus can talk to each other without the need of a router. However, with a managed switch, if you create virtual networks, or VLANs, and then each VLAN can only talk with the devices in their own VLAN, and they use the aid of a router if they need to talk to devices in another VLAN or another network. In this example, a device on VLAN 1 would need to send its request to the router, and then the router would send the request to the destination machine on VLAN 2. The receiving device on VLAN 2 would then send the response to the router, and then the router would send the response back to the device on VLAN 1. Even though both devices are on the same switch, they are now in two separate networks, and thus all communication between them must go through a router. Most home routers today are also wireless access points. A bridge is a device that manages traffic between two networks. A true bridge only has two ports, one on each of the two networks that it separates. Today, though, most networks just use routers, as routers can handle more than two networks. A bridge, like a switch, uses MAC addresses to make decisions. Many times a server is a standalone device and provides a single service, such as a web server. However, it can often happen that multiple services are provided by a single server. On larger networks, multiple services are needed to provide a single network service. On larger networks, multiple servers are needed to provide a single network service. For example, often you will have many web servers for a single website to handle all the traffic. Also, to allow for the website to stay up in case one of the servers fails and goes offline. Common network services provided by servers are web, mail, file, print, DHCP, DNS, proxy, authentications, and logs. All these are handled by network servers. And once again, on most networks, you'll need more than one server providing each of those services. So, example, you may have hundreds or even thousands of web servers providing access for a single website, and maybe even tens of thousands or hundreds of thousands, depending on the size. Think Facebook and Google and Amazon, they have thousands and thousands of servers to host just their main sites. Then you have mail, file, print. You can have multiple servers dealing with those, as well as your DHCP, DNS, logs. The syslog server or log server You could be sending all the logs from all your services to the log servers. So you may need hundreds, if not thousands, of log servers, depending on what you're doing. Unified Threat Management Appliance, UTM, is a new concept. It's considered a next generation firewall. It combines multiple security devices such as firewall, antivirus, identity-based access, intrusion detection, endpoint management, and virtual private networks, VPNs. It can include one or more of these services or all in one appliance. Once again, you may need multiple appliances depending on the size of your organization as well. The UTM, Unified Threat Management firewalls, are placed between the internet and the internal network. This depicts a laptop that is using the VPN service provided by the firewall, the UTM, to access the private network over the internet. Even though the laptop is located off-site and is connecting over the internet, they will appear to be located on the same private local network, just as if they were on-site at the company's office. That wraps up our talk on TCP and UDP. Next up, we'll be talking about Ethernet cables.